Okay, so I thought after that first session, why not have a bit more? Why not some more Haskell? You can't have enough Haskell, right? So I thought before we jump into the actual start of the course, the optional type, I just want to spend maybe the next half an hour or so just kind of you know going over this the ideas around or two ideas really, just kind of a bit more on algebraic data types and how they relate to functions, and then also just this idea of referential transparency, which is just a fancy name for pure functions, and kind of how that maps to types as well. Um, so I'm just going to spin up a REPL, and with Haskell, that's a really good tool called Stack, which makes these things working with the GHCI compiler a lot easier. But I'm just going to edit a file called values2 dot. Sweet. So, okay, I come to you and I say, look, loving these data types that are out in the wild. I love the bool, I love number, I love them all, but I want something a little bit simpler, right? I want something, less complicated. Can you give me a type that just has one value, right? I just want a type with one value. So I want some type called exactly one. It has one value. And I say, okay, cool, let's call this value solo, right? So what we've got here in Haskell is we're saying we have a type constructor called exactly one, right? So that's a type constructor with one value constructor, namely solo, right? And I'm just going to do deriving show, which basically to print anything out to the console, your type has to input. It's like an interface. Has to input like the show interface. But the Haskell compiler can just basically just generate that boilerplate for you if you just use the deriving keyword. So kind of forget that for now, but that's why it's there. So if we load values 2, we'll see that if I ask for the info for exactly once, exactly 1, it'll say, cool, exactly 1, right, is defined at line 2 of values of 2. And it's defined as this, with one value constructor. And if I ask for the type of solo, it says exactly 1, right? Right. So exactly 1 has one value. And I can show you what I mean by that is that if I had value, say, v equals solo, right? But is there any other value that let me say it another way, right? There is, if I want something of type exactly 1, there's only one way I can get a value that's of that type, right? And that is solo. There's no other value which is of type exactly 1, right? So, I hope that kind of that makes a little bit of sense. It kind of was weird because why would you want something of one value in the type, right? That's probably the only time where the type and the value are both 1. But even weirder question would be if I said, well, what would a function look like that has the type exactly 1 to exactly 1? Now if you think about what really are functions, right? Functions map some set of values to some set of output values, right? If you think about plus, for example, 1 plus 2 equals 3, what we're really saying is that plus takes two numbers and returns a number. It takes two values from the set of numbers and returns another value from the set of numbers. Right, so functions are really just, in a mathematical sense, they're just mappings. But what would this, I can give you the type and I can say, well, can you write me an implementation? Can you implement a function of this type? And it's really weird because you really only have one option, right? It takes an argument, A, and has to return something of type exactly 1, but only one thing. There's only one value that's of type exactly 1. And A can only be, usually a pattern match. If it was a Boolean, you'd say, well, true, do this, or if it's false, do this. But there's only one value that the argument could be, which is solo. So there's only one function that could exist for this type. And then you might say, well, surely if I maybe just add another exactly 1, there's more functions of the type exactly 1, taking 2 exactly 1s and returning exactly 1. And you think, all right, argument 1 and argument 2, and then I still have to return a solo. There's nothing else I can return. I can't return null or undefined. They're not in the type exactly 1. Only the value solo is in the type. So I have to return that. But then there's no choices for A1. A1 is type exactly 1, so it has to be solo. And A2 has to be solo. So this is the only function that can take 2 exactly 1s and return an exactly 1. So you can kind of see it doesn't matter how many times you played this game. You have 3 exactly 1s and returns an exactly 1. There's only one function that can implement. So you can kind of say this actually not that useful. This type isn't very useful because there's not much computation that we can perform over these types. And I've never really thought about it that way, but how many values you have in your type kind of is correlated to how useful your type is. And as I say that, it's not really true because there's properties of your type that's really useful. But in terms of the amount of computation, which sometimes you don't want, you want to be able to know, there's only X number of things I can do to this type. I don't want there to be almost an infinite amount of things. So yeah, power is how you look at it. But what I'm trying to lead to is this idea that, what's the next step up? We still want simple, right? But we want just a bit more complicated. And really, the next step up is the Boolean type, right? It's true or false. And let's imagine we didn't know about Booleans and we went, well, I've heard this thing called a bit, and I know that it can either be a 0 or a 1, right? And again, I'm just going to derive show. And now I ask the same question. Can you implement, I say I want a function that takes a bit to a bit. Can you implement a function that takes a bit to a bit? And I go, okay. Well, takes an argument A and I have to return a bit. But in this case, I can't just, in the case of exactly 1, I just return solo. But now I have to make a choice, right? Because a bit is either 0 or it's 1. So I've got to make a choice on whether I want to return 0 or 1. And whether I return 0 or 1 is also dependent on what A is. A could be 0 or it could be 1. So we just think about the left-hand side, for example, right? The arguments. We have to handle the case where it's 0, or we have to handle the case where it's 1. And then if it's 0, we have to make a choice. Do we want it to be 0, or do we want it to be 1? And so you can kind of now say there are more combinations about, there's more than one way to implement this function. But I might say, actually, you know what? It'd be handy if I had a function called bitNot that gives me the opposite. So if I have a 0, it gives me a 1, like I have here. And if I have a 1, it gives me a 0. Alright, that's pretty helpful. And if I load that, and I say, okay, bit not 0 gives me 1, and bit not 1 gives me 0. Well, that's kind of helpful. I've just implemented not. But if I said to you, okay, it's not as easy. If I said to you, all right, great, but how many functions are there? How many functions have the type bit to bit? And this is the weird thing, right? We can know this. We can calculate before time how many possible functions are there. How many possible functions? And if we think about it, we can very quickly do it for bit to bit, right? We could say, bit function 2. So in this case, I'm just going to say, when I get a 0, instead of returning 1, I'm going to return a 0, right? So this function now doesn't take the complement of the bit, doesn't give you the not bit. It actually kind of implements to 0. Like, doesn't matter what you give me, I'll always give you 0. Likewise, if I had bit function 3, well, I could say, instead of 0, 0, if you give me 1, I'll give you 1. And here, it kind of looks like we just implement the identity function, right? That given a 0, I'll always give you back what you give me. And that means there's actually only one more combination that we have left out, right? Which is, if you give me a 0, I'll give you a 1. If you give me a 1, I'll give you a 1. And this kind of means that we've implemented a 2, 1. And that's it. If we kind of grab that and put that there, they're all the functions that exist of type bit to bit. And that's it. It's kind of weird to think, but there's no more, there's no less. That's it. That's all the functions. You give them different names. You could, do whatever you like, but at the end of the day, that's the only 4 functions you have when you're going from bit to bit. And if we think about why that is, and maybe how much time? Oh, okay, I'll spend see if I can get this is kind of done in the next few minutes. All right, but we can kind of see what's going on here, that if I've got a function bit to bit, I'm always going to have, if it's 0, I have to make a choice. And if it's 1, I have to make a choice. So if I told you, hey, can you come along and fill this function out for me? Some function. If I said, oh, hey, I know you're busy, but can you come here and can you just fill out this function for me? I just need, I've got to go take a cup of tea. You go, well, if the argument is 0, then I have to make a choice. Do I want 0 here or do I want 1 here? And then once I choose here, I've got to go on and make the same choice here. So there's actually 2 choices I can make here, and there's 2 choices I can make here. And so basically what I can do is I can really say that the number of functions is the number of choices I have to make for each combination of argument, for each combination that the arguments could take on. And if we kind of go to a slightly more complicated example, what if I said, take 2 bits and return a bit, right? Which is, an operator, a binary operator will take 2 arguments and return, say like a Boolean binary operator, like or, would take, 2 Booleans and return a Boolean. That's, there's nothing special about, that operator. It's just that it has the type I take 2 booleans and I return a boolean. Here we take 2 bits and we return a bit. But if we think now about there's 2 arguments and we have to make a choice for the return value. Well, we know that it could be the case that it's 0, 0, right? Or it could be 0, 1. Or it could be 1, 0. Or it could be 1, 1, right? That's all the combinations that the 2 arguments could take on. And for each of these, again, it's the same game. If I said come here and make a choice, you have to say, well, I know there's 2 choices here. And then I know there's 2 choices here, here, and here. And so by the same logic, I've got 2 choices for the first one, 2 choices for the second one, 2 choices for the third one, and 2 choices for the fourth one. So I have 2 of the 4 choices, namely 16. So there, we've just seen it's only 16 functions that exist for bit to bit to bit, right? And it's not hard to see that bool is kind of the equivalent to our bit type, right? In fact, they are equivalent. You know, what makes a type isn't the name you give it or the name you assign to the values. It's the structure. It's how many values are there and what's the relationship between the values. In this case, the relationship is that you can only be true or false. In Boolean's case, in our case for bit, you can only be 1 or 0, right? So if we replaced, here, if we replace everywhere we used bit with bool, and everywhere we used 0, we said false, and 1, we said true. We can see that they're exactly the same, which means that there are only 16 functions that take 2 booleans and return a boolean, right? And functions of this type are or, and, an XOR, a not, and there's a bunch, but there's not there's only a bunch in the sense that there's a lot, but there's only 16 of them. There's a finite set. You can't just go and keep creating functions that take 2 bools and return a bool. There's a finite amount. And if you think about this 4 for a second, right? Where does this 4 come from? Well, the 4 is the number of combinations that we can make for the arguments to the function. So there's 2 times 2, right? The first boolean could be true or false. The second boolean could be true or false. So this is kind of the algebraic sense of this is partially why they call it algebraic types, because you can look at a type and you can start to do kind of like algebra on the types or the cardinality, how many values a type has to kind of work out how many functions could you possibly implement. And that's important because if you're doing pattern matching, you need to make sure that you've covered all the cases as a compiler. So that's kind of that's that. And again, we call these sum types. I'm just going to just delete that for a second. Okay, so that's sum types, right? And sum types is generally much easier to count how many functions you could have. But I just want to make it very clear that true and false here, or rather for our bit, zero is a data constructor and 1 is a data constructor, meaning that if I call 0, you can think of like a 0 argument function. It returns you a value, the value 0 itself. It's like a singleton. There's one instance of it. Because if we now think about product types, it's a little bit different in the sense that we may have if you think about now point, so we want this function called, this type called point. And I want point to have an x and a y, right? And I mean, I could say, to make it clearer, I could say x is int and y is int, and they're basically just called type aliases, but just for simplicity, I'm just going to have int and int. So a product type is a bit different. It doesn't say, this or this or this or this. It just says this and this and this and this. And in this case, we're saying it's int and int, as opposed to, int or int, right? I'm saying that so what's different between, one thing that's worth noticing is that, see how 0 and 1, they're the same, they're the same as make point. Both make point, 0 and 1, they're all value constructors, right? The difference is that 0 and 1 don't take any arguments, whereas make point takes 2 arguments, right? Takes 2 integers. You need 2 integers to be able to construct a point using the make point constructor. So again, I just need to write show so we can see it in the console. But now we can say something like point 1. If I load that up, doesn't like function. So now I can say something like make point 0, 0, stored in P1. And now P1 is make point 0, 0. Now what's interesting, if I said, well, what's the type of make point? What? It's just a function. It's like nothing else. It's just a function that says I need 2 integers and I give you back a point, right? Which is different to say the value constructor for, say, 0, which was just a bit, right? It didn't take any arguments. And so it's kind of like, because we need arguments to get a point, 0 is different in the sense it doesn't need no arguments. You just call 0, you get back a bit. You don't need to pass any arguments to get a point. Whereas make point, needs an argument. And if we partially apply a single argument, we can see that instead of now needing 2 ints to get a point, it just needs now 1 int to get a point. And so we could say the same thing here and say 1, right? And now we can see it's a bit ugly, but what this is really saying is that we first applied 0, we got a function back that needed another integer, we applied that, and now we get back a point with the coordinates 0, 1. Right, so constructors are just functions, and their arguments are, they need an int and an int in this case. So now you think about, let's bring it all together, right? So actually there's one more quick thing I'll mention is this idea of if I can spell referential transfer. This is just a fancy name for pure functions. And if we kind of look back to, say, our definition of bit not, right? The bit not has the type bit to bit, right? Which means, and this is a guarantee that you don't usually get in other languages, like TypeScript wouldn't give you this guarantee, or Java's type system, or even just primitive type systems like C. A lot of these type systems wouldn't give you this guarantee, but languages like Haskell and ML and kind of these certain type of type systems, pardon the type there, the type. Yeah, the nice thing about Haskell's type system is that when you say my function takes an int and returns an int, it can't do anything else, right? It can't print to the console, it can't make a network request, it can't wait for a user input, it can't do anything that you would kind of consider stateful or that has effects, right? It can only, like, the compiler will enforce. As soon as you try to do anything that has effects, the compiler will go, hang on, no, your type now is not bit, it's some other thing, right? And that's called referential transparency. It just means that it's pure in the sense that, while the same, if I give you a 0, I always return 1. I also always return 1, and I can't do anything else. I can only return 1. I can't do anything else. And this is important because a compile optimization that Haskell can make is that anytime it sees you've called the same thing repeatedly with the same arguments, it can just do it once and then go and replace it piecemeal, and just replace every instance that you've repeated the computation without worrying about, oh, well, actually every time you do that, make a network request, so it doesn't have this, it's not semantically the same. Like, it doesn't care. It just goes blindly just replaces them all because it has this property that it's safe to do so. And so that's kind of really important because, a lot of the reason you're doing Haskell is that you can literally most of the time just take if you have something on the left-hand side in some expression, usually you can just replace it yourself with what's on the right-hand side because these two things are always equal. Equality here means equality. It means 0 is bit not 1 and bit not 1 is 0, and there's nothing else to it, right? But kind of moving on from that, let's think about how do we combine the two types together. So if we have the classical example from OO, we might say, okay, I want a shape, I want to represent a shape, and I want to have, in OO sense, your superclass would be the shape, and then you have subclasses like rectangle and triangle and oval and whatever, and then they might all implement a surface area method that each subclass knows how to return the surface area. So how do we do the same thing with algebraic data types? So we might say we have a data type called shape, and let's just say it's a rectangle with a width and a height, or it's a circle with a radius. Actually, I'll make these doubles. Or it's a, let's say, triangle with a base and a height. And if you look at the type of rectangle, again, it's a constructor. It's a data constructor, and it says it's like, hey, I construct things of type shape, right? And if you ask the same thing of circle, it says, yeah, I also construct things of type shape. And theoretically, you could write your own constructor, but that's how you do it kind of. Well, actually, that's not quite true because you need to actually do it when you're defining data. But what we can think of a type is a set of constructors which will construct data or values for that particular type. And so rectangle says, well, I need 2 doubles to give you a shape. And circle says, well, I need 1 double. And the fact we have different constructors is semantically, a rectangle is different to a circle. And we want to be able to use that when we're pattern matching. So if I said, okay, cool, you've got this shape, can you compute the surface area for me? Which takes some shape and returns double, meaning the surface area as a double. And we might say, okay, so we get some shape. So the argument is a shape. And we've got to return some double. And this is where pattern matching comes into it, right? We could say, well, either you construct it with a rectangle, in which case I'll get the width and the height. Or you constructed it with the circle. In that case, I'll grab the radius. Or you constructed it with a triangle, which in that case, I'll get the base and the height. And so shape is actually a combination of a sum type and a product type, right? It's either rectangle or circle or triangle. Can't be both, right? So it's a sum type, but each sum type is a product type, where a rectangle is a double and a double. So here you can see that we've used both sum types and product types to create another type, which is the sum of product types. And that's why we know that this is exhaustive. There's no other way you can construct a value of type shape. So for width and height, to compute the surface area, we just got to times the width and height together. For circle, we need 2 times pi times, might be just pi times, what is it? Pi radius squared. And then for triangles, just the base times the height, divided by 2. And so if we look at the type for the surface area, we can see it takes a shape to a double. And we might say, well, what's the surface area of a rectangle that's 10 by 10? It's 100. What about a circle with radius 10? That doesn't seem right at all. I think I'm off by is it pi r? I'm sure it's pi r squared. No. Actually, that's probably right. Yeah, because that's the radius, not the diameter. That's fine. And so we can see here that we've used product types and sum types to construct shape. Now we construct functions, and then you can start to think about, well, how many functions are there of the same type as surface area? That take a shape to a double. So to answer that, you just need to know. Well, the problem is that there's so many different values of double, and that's actually quite a hard question to answer because double, there's a lot of values in the set of double. It's not as easy as the bit when there's only 2 values. But okay, but I think I'll probably just wrap it up there, right? Because I don't want to kind of blabber on too long. But I really just kind of wanted, before we jump into the optional type, in the Haskell course, the Data 61 course, I kind of just wanted to make sure that we kind of really understand what's going on here when it comes to data types, values, functions, and how they what's the relationship between them all, because most of the time when you're programming Haskell, you're doing this, right? You're defining data types and you're pattern matching depending on how it was constructed, and you're kind of constrained by the fact that when you say shape to double, the only thing you can do is return double. You can't do anything else. All right, so I hope that helped a little bit, but looking forward to the old map, because this is all cool, but I haven't even mentioned the fact that type constructors actually can take arguments too, but the arguments they take are types. So instead of just shape, take a rectangle having double, you could say, actually, I want to parameterize shape by AB, where rectangle is not of int, but I want to kind of generate a different type. So that's, you think you're kind of there, and then you realize, oh God, I can do this whole, I can give, types also arguments, and parameterize them, and that's kind of where, that's where we'll start when it comes to dealing with optionals. All right, I'm out.